So in today's session, I'm going to discuss on this example of root locus concept. So to further understand what is the concept of root locus method, we should consider the sort of example, which is by example, maybe it's easier for us by using numerical method like this. It is easier for us to understand actually what is the root locus concept or root locus method. So consider this block diagram. Actually, this block diagram is very similar to the previous one. Okay, very similar to the previous one. Because as you can see for this block diagram, for GS it is actually represented by K over S plus A, right? As you can see on my right hand side. So actually here K is a gain. So basically, if you can see for this particular block diagram, if you want to imagine that that block diagram should look like this, meaning that you should separate K with GS. Okay, suppose that there will be K block here and GS will be 1 over S plus A, right? Okay, so basically, based on this block diagram, with unity feedback, negative feedback block diagram of the control system here, as you can see on my right hand side here, I'm scrolling, which is, so I rewrite this block diagram and represent the value of K, sorry, represent the transfer function that is inside the block here, the transfer function represented by K over S plus A. Okay, so that is the transfer function, which is GS. So let's say GS is K over S and S plus A, right? Okay, we have this transfer function for this particular closed loop control system block diagram with negative feedback, and the feedback is unity. Let me draw some information from this control system block diagram. So if you have a look at this block diagram, we can say that the system has open loop transfer function of GS K over S plus A, meaning that we have the open loop transfer function, which is this part, which is the upper one. The upper one. We can say that the upper block, not the feedback one, the upper block, we can say that this is the open loop transfer function, actually. So that is the open loop transfer function, which is GS equals to K over S plus A. And then for that particular open loop transfer function, it should have the system parameters. We can see here the system parameters, which is K and A. K and A are the system parameters for that open loop transfer function. Okay. So K and A is the parameters where S is the variable. S is the S is sigma plus J omega, right? So S is the complex number, which is the frequency function. Okay. The third information we can draw from that block diagram, which which is given by GSK over S plus A, is the open loop transfer function has two poles. Okay, two poles, which is S equals to 0 and S equals to negative A. Poles meaning that we force the equation at the bottom line here, which is the characteristic equation, the denominator here, is if we make this S plus A equals to 0, we can say that the poles for this equation is the root of the characteristic equation, which is S equals to 0 and S equals to negative A. Okay, F equals to 0 and S equals to negative A, which is the root of this characteristic equation, the bottom line equation, right? So suppose that we can assume that for this particular control block diagram, the open loop transfer function has two poles, dual poles, which is S equals to 0 and S equals to negative A. How about zeros? How about zeros? There is no zeros because there is no S for the numerator. For the upper one, there is no S, meaning that if it has S, for example, S plus 1, meaning that the zeros is negative 1, right? That's what we have learned before, okay? If we force the if we force the numerator equation to 0, we make the numerator equation to 0 and we will get zeros. We will get zeros. S equals to something, meaning that that is zeros for this transfer function. All right. But in terms of stability, what we actually do is we focus on the characteristic equation, which is the bottom line, which is the characteristic equation lah, which is the denominator of the transfer function. So the open loop transfer function, we have S equals to 0, S equals to negative A. That sort of information actually we can draw from this closed loop plot diagram. All right. So let's say if we want to draw the root locus for that equation, the first thing what we should do is to find its transfer function. After this subtopic or after this section, actually, I'm going to talk about the rules. The rules when we sketch, the rules that we should follow when we want to sketch the locus, root locus. That rules is actually not we should follow, but actually it's a guideline when we want to draw the root locus, to sketch the root locus by hands. We can refer that guidelines. There are some equation to determine the break-even point, break-in, breakout point, and then the asymptotes, the straight lines in the locus, okay, the asymptotes, and a lot of things. There are 10 rules actually we should consider. I think some of the book shows some of the books present about 11 rules. Some of the book mention 10 rules. All right. So there are many rules to follow when we want to sketch a root locus for the closed loop system, closed loop control system. But for this case, we try to make it simple based on this. We are not going to one by one following the rules for sketching. But basically for this case, this is just a simple example, all right? to make sure that you understand the concept, we'll start with, let's say if we want to draw, if we want to sketch the root locus for this particular transfer function, we start with getting its we'd start with getting its transfer function of ys over us, okay? Actually, we can just transfer this, okay? You can just transfer this closed loop with unity feedback control system by this single block diagram, which is block diagram reduction that we have done before. For that particular closed loop system, basically we can get the block diagram of output of ys with input of us like this. So what is inside here is this equation. Is gs over 1 plus gs hs. All right. So we have learned this by using the equation. By actually we have done some proof. Proof of if we take the ratio or transfer function of ys to us, so we get the open loop transfer function, open loop block diagram like this, which is what is inside this block is actually gs over 1 plus gs hs. So since this is the unity feedback control system, suppose that hs is 1. Suppose that we have hs here, but in this case, it is a unity feedback, which is hs is 1. So basically, for the equation here, the transfer function of ys and qs, ys and ys divided by us transfer function, we can just substitute all of the values based on the equation that's been given. Let's say we use this equation, substitute gs and hs, so we get the following equation here. So this is gs, right? And 1 plus this is gs, hs is 1, okay? So basically times 1. Okay, and then we extend this, simplify it, this polynomials into this form, and then we can cancel s plus a here. So when we cancel s plus a, till we get this equation. So this is the equation of the transfer function ys over us for the closed loop. Closed loop system lah. This is the transfer function of the closed loop system of the block diagram just now. Of this block diagram. Okay, first thing first, what we do is to find the closed loop system transfer function, which is in this case hs is unity feedback, meaning that we can just substitute hs by 1, and gs is the equation that has been given here. Gs is k s over s plus a. So with that equation, substitute, and then till we get this form of equation, which is ys over us is k divided by s square plus as plus k. Okay. So the next procedure is actually to focus on this characteristic equation, which is denominator here. Denominator here is called the characteristic equation, which is the numerator, here. If there is s here, then we can determine its zeros, okay, for the numerator. But in this case, we just want to focus on the denominator, which is the characteristic equation. So for this characteristic equation, we can clearly see that this is the quadratic equation. Okay, for quadratic equation, suppose that we should have two roots, two roots for quadratic equation. S square, meaning that we should have two roots. We should expect two roots for quadratic equation. Okay, we should expect two roots for quadratic equation. So we should expect two roots for this characteristic equation. So how do we find these roots of the characteristic equation here? Basically we go back to the calculus to find the root of quadratic equation. We can just use this formula, negative b plus minus square root of b square minus 4ac divided by 2a, right? To find the roots of s. So substitute all these values, which is a is the, here a is 1 lah. Semua tahu kan? Kalau tak tahu ni, b is a, the constant a, and c is another constant k. Alright, so substitute all these values in this equation, then we end up in this s equals to negative a plus minus a square minus 4k divided by 2. And then we simplify it. We simplify this equation, okay, into this. So I rearrange this to further simplify this, right? Just to separate the real part and the imaginary part here. Okay. So we simplify this equation until we get negative a over 2 plus minus square root of a over 2 square minus k. So here we see that clearly we have two roots, two roots for this closed loop poles. For this closed loop characteristic equation, which is the roots, roots of that characteristic equation just now. So this is the complex roots, which is we call it as this as closed loop poles. So this is the closed loop poles. So finding the root for characteristic equation, we get this root, and this is actually the closed loop poles. So we have two closed loop poles, which is negative a by 2, negative a over 2 plus square root of a over 2 square minus k. And another one is negative a over 2 minus square root of a over 2 square minus k. So as you can see for this pole has two constants, two constant, which is K and S. Okay, to determine the value of S, we should substitute the value of K and S. Let's say if I assume that, not value of K and S here, value of K and A, depends on the parameters. Okay, the poles are depend on these parameters, which is K and A. So, in our beginning session last week as well, actually we try to vary the value of K. Okay, K is constant. K is something parameter something. We vary the value of K start from 0 to infinity to draw the root locus. But we have here A as another constant or parameter. Let us try to fix value of A. Okay, let's say we put A value as equals to 4. So let's say that A is equals to 4. Okay, just fix the one parameter here to make sure that there is, for this equation, we have only single parameter. And then if we fix A equals to 4, then we can vary the value of A. So we can vary the value of K, right? So assume that K is the system gain. Okay, suppose that K is system gain, and we substitute value of A equals to 4, then we end up to the equation of the roots here with single K. So we have the equation of roots or these poles with K as a gain. Okay, so single parameter. Now we can just vary the value of K. Since this is single parameter, we fix value of 4. We fix value of A equals to 4. Then we can vary the value of K. Let's say I have prepared this table. As you can see, we try to vary value of K start from 0, substitute the value of K as 0, 2, 3, 4, and so on until 13 here. You'll see that the poles values are changing. The poles values are changing. So, of course, we have two poles. As you can see, we have two poles. Let's say this is the imaginary axis. We have two pairs of poles, positive and negative. So positive and negative poles here at the imaginary axis. Okay. So sebelah kiri ini pole number 1 is referring to the positive roots of the imaginary, right? For pole number 2, suppose that this one. Okay, for pole number 2 is the bottom one, which is the negative imaginary. So we have two pairs, a pair of poles. Start from K equals to 0, we should have pole 1 as 0, pole 2 as negative 4. Okay. How do we get 0 and negative 4? Just refer to this equation. We substitute K equals to 0 for this equation. If I replace K with 0, then square root of 4 is 2. Okay. Negative 2 plus minus 2. For the positive one, pole number 1 here, this column, negative 2 plus 2, meaning that it is 0. For the pole number 2, negative 2 minus 2 is negative 4. That's what we do. And then substitute K equals to 2, and then we get negative 0.586 for the first pole and negative 3.414 for pole number 2. So you see that from K equals to 0, K equals to 2, 3, and 4 here, we get all of the pole values here are real number, right? No imaginary, are real number. See, pole number 1 and pole number 2 are all real number, meaning that poles exist on the real axis. Okay, untuk K sama dengan 0 sehingga K sama dengan 4, semua pole berada pada real axis. Okay, so for K equals to 0 till for K equals to 0 till 4 in this table, you can just draw the pole location start from 0, which is somewhere around there. Saya sepatutnya tunjuk dua-dua lah. Saya akan tunjuk dua-dua, table atas dengan diagram kat bawah ni. Okay. Yang ni pole yang pertama. Pole yang pertama pada 0. Pada 0. Pole yang kedua pada negatif 4 at real axis. Pole yang kedua pada negatif 4 at real axis. Itu untuk K sama dengan 0. Okay. That one is for K equals to 0. That one is for K equals to 0. Let's say I'm going to draw another pole. Sebab saya akan gunakan color kuning juga. Make sure you keep focus. I'm going to draw the location of the pole when K equals to 2, which is at negative 0.586. Where is it? Negative 0.586. It is somewhere here. Nampak? Somewhere around here, which is negative 0.586. Okay, for K equals to 2. And then another pole is, the location is negative 3.414. Negative 3.414, suppose that it's over there. So let me just put, which is, this is K equals to 0. K equals to 0 here. And this is K equals to 2. The second one, K equals to 2. And this is K equals to 2. Right? Okay. So we have finished the second one. Okay, we have started with K equals to 0 and K equals to 2. Now I want to draw the pole location for K equals to 3, which is the first pole is negative 1, the second pole is negative 3. So continue with this one, negative 1 and negative 3. That is for K equals to 3. That one also K equals to 3. For the fourth one, K equals to 4 is negative 2 and negative 2. So for the fourth one, actually we have 2 pangkah here. 2 cross. Because negative 2 and negative 2. Okay? 2 poles. That is redundant. Alright? So what we see actually up to 4, k equals to 4, we can expect that the pole is moving, pole location is moving from -4 to -2, right? Dia bergerak daripada -4 kepada -2. Yang sebelah kiri. Yang sebelah kanan, dia bergerak daripada 0 ke -2. It looks like that lah. Alright. So if we continue k equals to 5. If we continue k equals to 5, let me use different color. I'm still going to use same color, yellow one. When k equals to 5, let's see where is the pole location. The first pole will be -2 plus 1j. So -2 plus 1j is somewhere around there. And then -2 minus 1j is here. Alright. Then continue k equals to 8 and k equals to 13 until infinity. Alright. So until infinity, actually we can expect that the location will be moving toward infinity, just like that. Alright. So when k equals to 8, the pole location is right here. The pole location is right here and right there. Okay. Similarly, when we do for k equals to 13, the pole location is supposed to be right here and right there. Okay. Now we have all poles location for values of k varying from 0 to 13. We vary the value of k from 0 to 13. Suppose that we want to vary the value of k until infinity. We are not going to do that by hand calculation. With MATLAB, of course, we can do just by put some codings on that with MATLAB function of root locus MATLAB function. Then we will get the values until infinity. But for this case, since we are doing by hand calculation, we are not doing that until infinity, right? So up to 13, k equals to 13, you will see that the pole location is like that. And let we just draw the root locus, the loci or root locus of this particular pole's location. So we should start from k equals to 0 lah. We should start from k equals to 0 location, which is the open loop poles. K sama dengan kosong tu dipanggil open loop poles. We start from the open loop poles of 0 and 4. We start from open loop poles of 0 and -4 here. Let's say I start from 0. Okay, drawing from there. Then it will start from there. It will go upward like that. So that is the first locus. Then I'm going to draw with blue color for the second locus, second line. Since we have two roots for S, suppose that we should have two lines. So we should expect two lines of the root locus. So the second one start from closed loop poles of -4. Okay, toward that direction lah in this case. and then it will turn at -2, sambung ke arah bawah, sehinggalah sampai ke infinity. Sama juga yang atas, the same as the top one. So this is the root locus for this particular closed loop block diagram. Okay, with K equals to K over S plus A. We assume that for this particular root locus is for the case of A equals to 4. Huh? We fix A equals to 4 and we vary K from 0 to infinity. Okay, so this is the root locus that we have. Huh? Okay, so this is a simple example for you to keep practice on how to draw root locus. Huh? Basically, you just can do the self-study and just slowly follow all of this method. Follow this method. Okay, do it one by one. Estimating the value of poles, the poles here with varying the value of K. Then locate the pole location on S-plane and then draw the lines so that till you get the root locus. Okay. So if we continue with higher K, it will result in higher poles data. Okay, if we keep varying the value of K, I have just mentioned just now, if we keep substituting the value of K until infinity, then we can expect that the root locus is moving toward infinity. Okay, for the first locus, start from 0, it will turn and moving toward infinity. For the bottom, for the blue one also, it start from -4, from poles to zeros. Okay, kita nampak kat sini daripada poles ke 0. Sama juga yang ni daripada open loop poles of 0, daripada kosong ke daripada poles ini pole location ke arah zeros. Okay. Katalah kalau 0 ada kat sini, dia akan pergi ke 0 tu lah. Itu antara rules yang kita perlu pelajari lepas ni. But basically for this case, you will expect the locus is like that. So in control system design and analysis, we can do some interpretation. How do we interpret this root locus method? The first thing is we can, in control system design analysis, the first thing is about transient response behavior. Okay, we can determine the poles that give the desired damping ratio. Damping ratio is the thing that we want to evaluate when we do the root locus technique, right? And then also the natural frequency. Damping is something like that. Natural frequency is like that, right? We have learned this. So if we combine these two, suppose that it should have exponential function and the oscillatory behavior like that, the sinusoidal function. Okay. The second one, note that the root locus started at 2 points, which is -4 and 0. Okay, it started from 0 and -4 when K equals to 0, right? On the real axis, and moving toward point -2 sehingga -2 dekat real axis ni, dia daripada kosong, daripada -4 dia pergi ke arah -2, point -2 dekat real axis. Yang ni pun sama, pergi ke sini dan dia break out. Dia break out. Okay, break out ke arah complex plane, ke arah J omega, sehinggalah bila K tu mencecah infinity, then kita dapat nampak satu ke atas, satu ke bawah sehingga infinity. And then the third one is we start the locus at open loop poles. We call the open loop poles when K equals to 0, which is the open loop poles for this case is -4 and 0. But the complete plot is proved to be closed loop poles. Kita mula daripada open loop poles, kosong dengan -4. Kat mana kita nak tahu open loop poles? Awal-awal lagi kita dah tunjuk kat sini. Open loop pole, open loop transfer function has two poles. Open loop ada dua poles. Pada S sama dengan kosong, pada S sama dengan -A. Remember, we fix the value of A of 4. A equals to 4. So, kosong dengan -4 lah. Alright. Okay, that is for the statement of number 3. So, we have open loop pole of -4 and 0. Okay. So, what we can say based on our sketching just now of the root locus, we can say that root locus is a graphical method. When we do sketching, we represent it in terms of graphic. Okay, gambar atau graphic. Gambar. We represent in terms of that S-plane punya tu sebagai graphical method of obtaining the closed loop poles and zeros. It shows the behavior of closed loop poles as the system parameters gain increase from 0 to infinity. Okay. So I will leave some exercise for all of you to do later. So maybe I will make it properly in your e-learning system so that you can submit this exercise 5.1. We have ada dua. A apabila GSK over S plus 2. B GSK over S plus 2 square. So yang ni answer hints. Answer hints. So you can see the answer hints here. But what I would like to see is your method of calculation till you prove that this is your sketching of root locus. Alright. So I will post this later in your e-learning system. But for the time being, since you have these lecture notes and also you will watch this video later, so I think you can just start from now lah to prepare your answer. Okay, I will release the exercise later. Okay, so for this session, I will finish up to this time, which is 9:59. 1 minute before we end, so I would like to stop right here so that you can continue your next class.